Welcome to the fifth lecture of the mini course on zoology of excitons. This time we're going to talk about ligand field excitons, which are probably the most exotic variety that we will have encountered yet. And I would argue it's fairly hard to find sort of introductory information about this concept. I'll give you a couple of references as we go through, but this is even a terminology that I would say is not super common. So what we're going to talk about is how to make an exciton on a single ion site. I'm thinking about in a solid. I suppose that's not absolutely essential. I suppose you could think about it in a solution or even the gas phase if you wanted, but for me, as a condensed matter physicist, I'm always thinking about a solid. And so we're going to focus on transition metal compounds, which have partially filled d orbitals. And so that's a place where optical excitation can sort of be localized on a single ionic site. Our basic case study throughout this lecture will be chromium trichloride, which is a beautiful purple compound that I'm actually working on in my lab over the past several years. And so just to remind you, this is kind of our pictorial framework for the different types of excitons in the zoological study. And we're sort of categorizing it by a combination of binding energy and average exciton radius, or exciton size, where the idea is that those two are somewhat correlated in that if you have a larger exciton size, you'll tend to have a smaller exciton binding energy. And so as we approach the Frankel exciton regime that we talked about with the molecular excitons in the last lecture, you definitely get to a situation where this simple correlation where binding energy goes as 1 over the average radius is not obviously going to be maintained, right? And then in particular, as we cross below the threshold of being separated by a single lattice site, we're into the regime that we're going to talk about today, D to D excitons and other more exotic types we'll talk about later, where it's really unclear whether you should even maintain this hydrogenic picture at all. But in any case, I claim that the hydrogenic picture is always good as a sort of starting point for discussing even very large deviations from the ideas. So what we need to do first is have a little bit of a crash course in ligand field theory. It's possible that people would have encountered this in their general chemistry course, but maybe not necessarily. I know I did. And I've spent a lot of time thinking about it as I've built my research group. And so it's actually a really interesting topic, especially if you are a condensed matter physicist. I think it gives you a little bit of a different perspective on some topics in solid state. But in any case, we want to start with the idea that if you have an ion in free space, say a chromium 3+ ion, where this is sort of the typical cationic state of chromium in most solids, or not, well, I don't want to say most, but in a lot of solids. And so you've got 5d orbitals on this ion, and in free space, it's totally spherically symmetrical. And so the 5 different m sub L quantum numbers are all degenerate. And so you would write the electron configuration, this is just review, as an argon core, and then in the 3+ cation you have just 3 electrons here in the 3D valence shell. And so if you know Hund's rules, you know how to fill up the 5 degenerate m sub L values. You tend to maximize the spin, then you tend to maximize the total angular momentum, and then you sort of ask the question of, well, is it more than half full or less than half full to determine whether you have an L plus S or an L minus S. And so that's actually maybe something that, if you're feeling uncomfortable with some of the things I'm saying today, you may want to go back and review Hund's rules from, say, a modern physics course, or again, possibly a general chemistry course. Because, probably a lot of things won't make a ton of sense today if you're not somewhat familiar with Hund's rules. But now we're going to ask a question. In a molecule or a solid, we're going to break the full 3D symmetry around the chromium ion. And so we can sort of think about that as, let's just make chromium trichloride, which locally around any given chromium ion, you're going to have 6 chloride ions. And they're arranged almost in an octahedron. So this is very, very symmetric, but it's not the full rotation symmetry of free space. It's called the octahedral point group. And anytime you break a symmetry in quantum mechanics, you also break up that degeneracy. And the octahedral case is probably the most important for thinking about ligand field theory, OH point group. And so the idea here is somehow that if you would just consider looking down from the top, so say the vertical chloride here is the z-axis. So let's look down onto the xy plane. You see that the dx squared minus y squared orbitals are sort of directed right at the chloride ligands, whereas the dxy their lobes are located in between. And your intuition sort of comes from the electrostatic repulsion perspective on this, even though that's not necessarily like the final story in ligand field theory. It is a molecular orbital-based theory, not just an electrostatic-based theory. But the intuition from electrostatics is correct, that you can sort of imagine any electrons in those d orbitals will be more strongly repelled in the x squared minus y squared orbital compared to the xy. Right? And so this would tend to be higher energy than this, and that gives us a clue about how to break this degeneracy. And so the idea is you break the 5 d orbitals up into 2 separate sets of orbitals, threefold degenerate xy, xz, yz. So that's like this one where all the lobes are in between the ligands, and then the z squared and the y squared are directly directed right at the ligands, and so they're higher energy. And so in terms of like a chemical intuition for what's going on here, the T2G orbital set is essentially non-bonding. There, no net contribution to bonding between the metal and the ligand. And then the EG is a little bit anti-bonding, so slightly destabilizing to the molecule. Yeah, so the important point is breaking the degeneracy into these 2 sets, and then we need to place all of our electrons in, and so again, we're just going to follow Hund's rules, where we would fill the lowest first, we'll maximize spin, we'll think a little bit about orbital angular momentum, maybe that's not so important right now, and so we just put them all 3 into the lowest T2G set with spins pointing in the same direction, schematically. And so this is the ground state of the chromium 3 plus ion. And we call the difference in energy between the T2G and the EG the ligand field splitting. Again, this is mostly review from like a general chemistry course. But now let's keep going a little bit further than you would probably go in general chemistry and start to talk about some group theory notation for how we discuss these configurations. So this, as I've drawn it here, is a configuration associated with the ground state of the chromium 3 plus ion. And so the total spin for having all 3 of these sort of spin aligned according to Hund's rule will be 3/2. And so the spin degeneracy in the ground state is 4-fold. That's called a quartet. So we would consider this configuration to be orbitally, I'll call it orbitally non-degenerate, because basically there's only one way to half fill this shell. You can't like choose a different set of 3 to occupy because there's only 3. And so that is written in a group theory notation in the following way. You put the spin degeneracy on a left superscript, so that's 2s plus 1. You talk about the sort of orbital or configuration-based degeneracy with a big letter that's associated sort of with the group theory term symbol. And so A is fully symmetric or non-degenerate. And then you sometimes put a right subscript, again associated with the group theory character table and any possible inversion centers. So, I think this notation is used a lot, and it's important to be somewhat familiar with it. I don't know how much I would recommend spending time learning it perfectly. But the thing that's important for me to say is that, the term symbol quartet A1G, that's how you would read this, is associated with a configuration. And sometimes the configuration is more helpful to draw and think about than just the term symbol. And so in this case, the association of quartet A1G is unique. There's only one you can actually draw. But it's actually not necessarily the case that there's only one configuration for a given term symbol. We'll see that in the next slide. And so that's just a distinction that actually helps me to think about this, is that this picture is T2G with 3 electrons in it. That's a configuration. And then the term symbol is sort of a group theory character table reference that tells you about sort of how to use a group theory character table to deal with this configuration. But what we need to do now is talk about the excited states you can make, specifically like how could you make excitons in a system where the valence electrons are, say, in the T2Gs like this. So let's start with this ground state, and let's remind about the sort of spatial orientation of the different d orbitals. xy, xz, yz, dz squared, dx squared minus y squared. And so it's fairly obvious that the simplest excitation we can make is to go from the dxy into one of the two EG orbitals. And so as drawn, it looks like it would cost the same amount of energy to go into either one. But that's a bit of an oversimplification of drawing this ligand field splitting diagram. And in fact, it's not the same to go into either one. And so what we've shown here is the lowest energy excitation if you would, say, start with the dxy electron and ask where's the lowest energy place to put it. And so the lowest energy place to put it is to kind of keep it as close to itself as you possibly can, and that means put it in the dx squared minus y squared. If by contrast you decided to put it in the other one, you would be putting more electron density along the z-axis, which would increase the electron-electron repulsions with these two remaining ones. And so this is actually moving this from here to here is not the same as moving it from here to here. Okay. And so this configuration that I've just drawn is one of the quartet T2G configurations. And there are two others. That's the origin of the letter T in the term symbol. It's a triply degenerate configuration. And that's because I could choose to start with any of these 3 T2G electrons and put them up into their appropriate EG that minimizes their repulsions with the remaining T2G electrons. So just to show you, if I instead had chosen dxz, I would not want to put it in the x squared minus y squared with the after excitation, because that would now enhance repulsions with xy and yz. But if I do put it in z squared, that's the lowest energy excitation I can make, because it sort of leaves the electron density minimally altered compared to the ground state. And the same would be true if I chose to do from the yz. Again, I would not want to go to x squared minus y squared. I would rather go to dz squared. So those are all 3 of the configurations associated with quartet T2G states. So yeah, then the next example is the next highest excitation in this system would be if instead of taking xy and going to x squared minus y squared, I would take xy and go to z squared. And that also is triply degenerate because I can go back and do any one of these three as the starting point. And this is called the quartet T1G. To be honest, I don't know why we start with 2 and go to 1. Again, those are all connected with sort of the conventional octahedral point group character tables. And I don't find it very useful to think much beyond that. That's just how they make the symbols in the character table. But it's important that these are not the same energy, right? There are electron-electron repulsions in this problem, and so if you do want to understand how these different configurations appear in terms of their energy hierarchy, you do have to recognize that electron-electron repulsions are real. And so the lowest energy excitation is quartet A2G to quartet T2G. All right, so that would be just an example is this one. Just picked one of the configurations to show, even though there are 3 possible that are all degenerate. And I think the important other thing to keep in mind is that these optical excitations do need to obey the spin selection rule. So if you remember when we talked about singlet to triplet excitations being spin forbidden, the same holds true for any spin multiplicity, right? So if I start with a quartet, the optically allowed absorptions are only into quartet states. There are other configurations associated with these d electrons, but they are spin forbidden, and so they're not very important in terms of the optical absorption. But they are important in terms of the overall optical properties, and we'll say a few more words about that in a minute, and also maybe in a future lecture. And so the idea is that if you do make this quartet A to quartet T excitation, now on a single ion you have an electron in the EG, a hole left behind in the T2G, and that is what I would like to call the ligand field exciton. And so just as an example, let's take a look at some chromium 3+ compound absorption spectra. So here's a relatively recent paper where they present spectra of potassium chromium oxalate, coordination compound. And so what you can see is that there's a intense low energy bump at 570, another one at 420, and those are assigned as the 2 quartets, right? The lowest energy one and the little bit highest energy one. And then interestingly, you can see a weak absorption down on the leading edge of the quartet 2 that is assigned as the doublet E, which is a different configuration that is spin forbidden but still has a really weak absorption in this particular compound. And so the way that chemists analyze these absorption spectra is through what's called a Tanabe-Sugano diagram. And it shows the ground state essentially as a horizontal line on this axis. So it's labeled here as quartet A2. This is from another JChem Ed reference from the 60s. And so here they even list some notation for the configuration, that this is a triplet occupation of d orbitals. And then they show the important term symbols and how their energies relative to a parameter called B vary with ligand field strength, dq, again in units of B. And so what's important about this? A couple things. This is sort of a semi-empirical diagram. In the sort of in the sense that there's a lot of model assumptions that go into it. But the other thing that I do think is important about this diagram is the B parameter includes significant contributions of electron-electron repulsions. All right, and so this diagram does have a lot of the important physics associated with D to D excitations already inside it through this B parameter, and obviously through the DQ parameter, which is the ligand field splitting. And so here it's basically showing you start in a quartet, and the first thing you would want to do is look for what are the lowest energy quartets you could excite into, right? And so you would basically find the value of DQ that is appropriate to you, and then you would sort of go up and be like, okay, what's the first quartet I run into? And okay, it's the quartet 4, or this value of DQ. And so that's the first spin allowed transition, and that would have this energy, again, in units of B. And then there would be another one pretty close by if you went up, right? And so these 3, 1, 2, and 3, are all doublets. So they're spin forbidden. And so here you can see the doublet E, which is basically not an excitation across a ligand field gap. It's actually a spin flip excitation. And we'll talk about that maybe later on. But from the standpoint of like what are the main absorptions, you're looking for quartet, quartet, quartet. There's another doublet that's not spin allowed. There should be another one way up here, right? And that presumably is this UV peak that is not seen very clearly in the data. So yeah, the characteristic that you sort of pull out from the Tanabe-Sugano diagram here is that chromium 3+ compounds should have 2 broad peaks associated with quartet-quartet absorptions, and that you can sort of figure out ligand field splittings and maybe something about the B parameters by using these diagrams. So Tanabe-Sugano diagrams, I guess, are like an inorganic chemistry topic. And so it's fairly easy to learn how to use them. I'm not really trying to give a little tutorial on them right now. I'm sort of just pointing out those, the way you hunt for spin-allowed transitions inside these things. But they are a very important tool for analyzing real data. So here's an example of, again, chromium trichloride, which is an interesting compound from the standpoint of 2D magnetic materials research. And so on the left side, you see some data from our lab, which shows, again, these 2 peaks in absorption in black, which you can associate with the quartets, the quartet absorptions. And then I'm also showing the emission from the quartet in red, which is pretty interesting in the sense that it's way more narrow than the absorption. It's still quite broad, but it is more narrow than the absorption. We can go back to 1970 and see the absorption spectra. This may have been one of the first ones published for chromium trichloride solids, again, where you can see these broad absorptions with the double peak structure. And in this case, it was already pointed out that the width of the absorption is sort of too broad to just be simply vibrational broadening, vibronic structure of the chromium trichloride molecule, if you want. And instead, what's happening is there's substantial broadening in the absorption that comes from trigonal distortion. So the octahedral symmetry around the chromium 3+ is not perfect. It's actually substantially distorted, and that gives rise to a more complex structure in the absorption spectra. Nevertheless, starting from the octahedral symmetry perspective is a good way to understand, okay, why do I have 2 peaks, and why are there sort of peak centroids separated by a certain amount? And then when you need to go in and analyze the fine structure, as Polini and Spinolo have done, you need to think about the distortions from perfect octahedral symmetry. And so this data that I'm showing you on the left is from, again, my group, and this is a part of Sam Sridhar's PhD thesis work. Yep. So yeah, we just assign quartets, no problem. And so I think this is really interesting because these are the smallest excitons we have considered. And you could probably debate whether it's even beneficial to call them excitons. So what do you even call the size? Should you use a hydrogenic model? And if so, what is the dielectric constant if it's a single ion? And then probably the most interesting and hopefully practical question is, can these types of excitons be used for anything in a solid? Can we transport energy? Can we make solar cells? Can we make photoconductors, et cetera, et cetera? And so where do we put them in our map of the excitons? Down here, again, do we put them where their size is about a lattice constant, or is it a little bit less? It's honestly hard to know. But luckily, there's been a fairly sophisticated theoretical study of the excitons in chromium trichloride recently. And so here is a picture from Zhu and Yang in 2020 where they show the exciton wave function. In this case, it's in a monolayer of chromium trichloride. And each of these blue circles is a chromium ion, and the green ones are chloride ions. And so what you can sort of see is that the ligand field exciton wave function is mostly localized on this central chromium cation. And it extends somewhat anisotropically in a couple of directions, but typical size is of order 1 lattice spacing. So it's fairly small. It's not a charge transfer exciton in any way. There's no real charge is not transferred between two different objects in this excited state. But it's still true that the size of the exciton is about a lattice spacing based on this analysis. And so when you look at their calculations, which are, it's called a beta salpeter equation, which is one of the modern ways of calculating from first principles optical properties of solids. In their beta salpeter analysis, they get exciton binding energies of 3 eV for the monolayer and 2 eV for the bulk. So again, there's this expected difference in binding between monolayer and bulk that we already talked about with the molybdenum disulfide case. And so let's just take a look at how this would arise in a hydrogenic picture. Again, these calculations are more sophisticated than a hydrogenic model. But what do we understand by looking at the hydrogenic model, say with a chromium-chromium distance of 0.346 nanometers? So if I just plug that in with the sort of hydrogenic formulas that we have, we end up being able to calculate the effective mass directly from the estimated radius, and getting that the effective mass is about half of the electron mass. Right? So again, solve for mu given this as a parameter from the Zhu paper. And then plug that in here with the dielectric constant of chromium trichloride, and you get minus 0.6 eV. So it's not quite right for 3D, but if you had a monolayer, you would need to increase it, and you'd get a little bit closer. And so what is sort of wrong here? I think there's a couple things we need to be suspicious about in this analysis, and the hope is that it's informative to find the places where this analysis is suspicious, right? So I don't think there's anything suspicious about using the size calculated from the beta salpeter analysis. That should be fine. Perhaps there's something suspicious about using epsilon equals 3.5. Why would you choose to use what is sort of a macroscopic materials parameter to describe electron-hole interactions on a single ion site? Perhaps it would be better to use a smaller value. Maybe you should even just use the bare dielectric constant of vacuum in this case. That's one thing that I have been thinking about, is that it might be better to just use epsilon equals 1. So then what? You would get a smaller effective mass by a factor of 3. So that actually goes in the wrong direction. But then at the same time, you would be dividing by a much smaller number in calculating the binding energy, and it might come out quite a bit closer. So that would be a cool thing for people watching this video to just stop and check and see what they think. So I think the dielectric constant is a suspicious point. But there's even another suspicious point, and that is estimating the effective mass using the radius is a bit suspicious. And even if we go to the Zhu paper, or sorry, not the Zhu paper, this is a new theory paper by Acharya that talks about effective masses in the chromium trihalide materials. And they are quite a bit larger than the 1/2 that we got from that size. And moreover, they're anisotropic. And so I think this is probably a place where I'm quite certain our analysis is flawed. All right, where we absolutely do not have accurate effective masses just using the hydrogenic model to assess effective mass. And so these are strongly correlated materials. The D bands are very narrow, and you really would not expect the effective mass of electrons in such narrow D bands to be smaller than the free electron mass. In fact, you would expect it to be bigger, and indeed this paper shows that it is. So this is probably the most important thing to think about, is that if we did use these effective masses in the exciton binding energy formula, we would probably get much better agreement with the beta salpeter binding energies from Zhu et al. And so, again, I think, does the hydrogenic model apply here? I think that's maybe not the interesting question. I think the interesting question is, in what ways does simple application of the hydrogenic model fail? And that probably tells you cool things about these excitons. And so again, effective mass in these exotic solids with correlated electrons is going to be really important to get right. And then when you have really localized excitons, it's somewhat unclear what do you mean by dielectric constant. So this is a really important part of the 2D materials community right now. Since about 2017, Xiaodong Zhu's group at the University of Washington has been studying the chromium trihalide materials in single monolayer form. They began with chromium triiodide. And one of the things that they found was that you can actually get circularly polarized photoluminescence from chromium triiodide monolayers when it is in its ferromagnetic state. And so this is a really interesting and beautiful correlation between magnetic ordering and optical properties that's connected to the D to D nature of the ligand field excitons in this material. And so this paper from Saylor et al. Talks about this circular polarization effect, and also shows some very nice spectra that illustrate a lot of the things we've been talking about, namely absorptions into the quartets, the broad photoluminescence. Notably, there's this Stokes shift between the absorption and the photoluminescence. And so this is a really interesting opportunity for sort of thinking about these more unusual exciton varieties in novel magneto-optics applications. And so what we've done here is to sort of start to fill in this very bizarre region of our map where the size of the exciton is starting to be a little bit meaningless almost. But in any case, it might be of order or somewhat less than a lattice spacing. And we've sort of associated this exciton with a single ion. So this is an electron hole pair that is not separated by 10 or 20 atoms or whatever like we started at the beginning of the discussion, but rather electron hole pair on this single ion site. I don't even know how to draw it, but I roughly made a little oval that sort of looks like the Zhu et al. Beta saltpeter paper, but mainly is just meant to indicate that this is quite small and unusual. And I think it's really fun to think about how to connect these type of excitations with other degrees of freedom like magnetism. And so we're going to keep going with this in subsequent lectures where we talk about other types of D to D excitons, including Maude Hubbard excitons and spin orbit excitons. And we're all going to be kind of sitting in this very unusual region where the size of the exciton is maybe slightly less than or about equal to a lattice spacing.